In order to understand the Big Bang Hypernova hypothesis, we need to understand the two parts of its name. Firstly, there is the Big Bang part of the name. The Big Bang theory is a story told by science as to how our universe was born into existence around 13.8 billion years ago. According to the Big Bang theory, our universe was born from an infinitely hot and dense singular point named the primordial atom. Outside of this singular point, there is nothing, neither space, time, or matter. Everything that has existed and will be was contained to being inside that one singular point, infinitely small and infinitely dense. How or why this came to be is the question that modern physics searches for in order to complete our understanding of nature. The Big Bang Hypernova hypothesis is such a quest that radically challenges this long-standing and established idea of the primordial atom. However, before we can challenge the idea of the primordial atom, we first need to understand some of the history, science, and evidence regarding the Big Bang theory. A key pillar that led to the formulation of the Big Bang theory was the observed expansion of space-time. As first demonstrated by Newton, light, when passed through a prism, is broken up to reveal the individual wavelengths of light. Dependent upon the elements whose reaction causes the emission of light, which is then passed through a prism, we see fixed patterns of dark lines visible on the resultant spectral map. By studying these spectral absorption lines, we are able to determine and work out which elements of the periodic table were involved in the creation and emission of light from the given source. For instance, in the most simple case, we can see the spectral lines denoting hydrogen gas as being responsible for the light source. Another example comes from the yellowish sodium halogen lights used for street lighting at night time. Here, we can see the absorption lines caused by the element sodium. So by passing light from a distant star through a prism, we are able to see and measure the star's spectral absorption lines. By knowing what spectral absorption lines are produced for each of the different elements of the periodic table, we are thus able to determine what composition of elements make up that distant star. This is an experimental technique known as spectroscopy. At the turn of the 20th century, astronomers came to realize that what had first been observed as fuzzy clouds or nebula of light were in actual fact separate galaxies from our own. In fact, up to this point in time, we believed that the entire universe was just our Milky Way galaxy. The observation of these new galaxies greatly expanded our vision of the cosmos, such that over a century later, we understand that our galaxy is just one of trillions of galaxies in an ever-expanding universe. But it was in the spectral absorption lines and the light from these remote galaxies that we learnt that the universe was in actual fact expanding. In 1912, the astronomer Vesto Slipher, using spectroscopy, discovered something extremely unusual in the spectral absorption lines and light coming from remote galaxies. That was, the spectral absorption lines had all been shifted down towards the red end of the spectrum, hence where we get the name, redshifted, in talking about the distance a galaxy is from us. A decade later, in 1922, Alexander Friedmann, using Albert Einstein's field equations of general relativity, provided a theoretical basis that the universe is expanding. This theoretical expansion was then used to provide an explanation as to the observation that light from remote galaxies was significantly redshifted. In talking about space and time, with respect to general relativity, it is described as being like a single fabric that we simply call space-time. That is, both the three spatial dimensions, up, down, left, right, forwards, backwards, and the one temporal dimension of time, are in fact one whole four-dimensional system that we call space-time. We describe space-time as being like a fabric in that it can be bent, curved, and shaped by the presence of mass. This relationship between mass and the curvature of space-time is what is described by Einstein's field equations and is general relativity. So in describing the expansion of space-time, we can think of it as being like an elastic fabric that is constantly being stretched. A length that measured a meter in the early universe would stretch and expand over time until it is 2 meters long, and then later 3 meters, and so on. Or more specifically, the light emitted from a distant galaxy starts its billion-year journey to our telescope here on Earth. When the light starts its journey, its spectral absorption lines are not shifted. A 600 nanometer wavelength of light measures exactly that, 600 nanometers, when the light starts its billion-year-long journey. But as Alexander Friedmann discovered, by Einstein's equations of general relativity, that because the fabric of space-time itself is expanding, that the wavelengths of light are themselves being expanded. So, our original 600 nanometer wavelength would expand to 650 nanometers and then to 700 nanometers, and so on as time progressed. Thus, our yellow light, with a wavelength of 600 nanometers, first turns orange and then red. So when the light from the distant galaxy reaches us, a billion years later, it has been stretched out, such that it has now been redshifted because of the expansion of the fabric of space-time. If any person can really be credited with inventing the Big Bang theory, it was Georges Lemaître. In 1927, Georges Lemaître independently reached a similar conclusion to Friedmann by studying Einstein's field equations. That was that the universe is expanding and travelling away, receding from one another because of the expansion of the fabric of space-time. In his work, Georges Lemaître presented the first observational evidence for a linear relationship between distance to galaxies and their recessional velocity. Georges Lemaître approached Albert Einstein at the 5th Solvay Physics Conference in 1927 in order to discuss his paper. Einstein had no comments regarding Lemaître's mathematics as it was technically perfect. It was Einstein's belief at the time that the universe was static and that it had always existed that caused Einstein to dismiss Lemaître's ideas. Also known as the steady-state cosmological model, the predominant idea at the time viewed the universe as eternal with no beginning nor end. However, it was through the careful and diligent work of Edwin Hubble, who confirmed Lemaître's work, that caused Einstein to change his mind, that the universe was not static, but in actual fact was indeed expanding. A consequence of an expanding universe is that when you reverse time and run the clocks back, it was found that the galaxies come together. Thus, as a logical conclusion, if we ran the clocks back far enough, we would see all the galaxies come together, with all of them coming from the same point. Following this conclusion, Georges Lemaître in 1931 formulated the first revision of the Big Bang theory. By rewinding the clock back, Lemaître realized that the metric of space-time would grow smaller and smaller. As a result, the galaxies would come together and the universe would become hotter and denser as it became smaller and smaller. Taking this to its most logical conclusion, Lemaître formulated the idea of the primordial atom, which he published in a seminal letter to Nature entitled The Beginning of the World from the Point of View of Quantum Mechanics. This, in effect, was the beginning of the Big Bang theory as we know it today. The primordial atom, as Lemaître envisioned it, was like a massive atomic nucleus, such as uranium, using the newly developed theory of quantum mechanics. Like a massive atomic nucleus, Lemaître's primordial atom is unstable and splits, which in turn again splits over and over again, giving birth to all matter, energy, space, and time. Georges Lemaître, like Aimé Noether, for me is one of those scientists whose ideas and contributions have been overshadowed and only now are truly being appreciated and celebrated. As an aside, Aimé Noether, one of the greatest physicists and mathematicians of the early 20th century, whose elegant and beautiful proofs showed the mathematical relationship between symmetry and conservation laws, is a subject for another episode, particularly when we come to look at charge parity time symmetry and the theoretical consequence of a parallel universe of antimatter, or as I like to say, it's in that other jet. To me, Lemaître was a true genius, whose work and contributions are only now being celebrated. For instance, the linear relationship between the recessional velocity of galaxies and its distance from us has been for a long time called Hubble's law, after Edwin Hubble. But it was in fact Lemaître who first showed this relationship. But for various historical reasons, like the famous encounter between Einstein and Hubble, as well as Lemaître's work being written in French, saw Lemaître for a long time being overlooked in the Anglosphere. Lemaître, as well as being the first to show this linear relationship regarding the expansion of our universe, in addition, laid out the initial theoretical framework for the Big Bang theory. Employing the new ideas of radioactivity and quantum theory, he described the primeval atom as being a single atom whose nucleus contained all the protons and neutrons that now make up our universe. All of nature was contained within a single massive atomic nucleus. Radioactive decay, being random and hence invariant to time, caused the primeval atom to decay and split. For without time, which requires space, because as Einstein showed, it is in fact space-time, there had to be a mechanism by which time could actually start, and that mechanism was for Lemaître radioactive decay. Having independently walked down the road of researching and developing my own independent cosmological model, that in reading about Lemaître's inspiration for the primordial atom, or rather primeval atom, the first atom, was almost pure genius to my eyes. On the one hand, after nearly a century of unparalleled scientific discovery, Lemaître's vision of the primeval atom being like a massive atomic nucleus that continuously undergoes nuclear fission, splitting over and over again, seems naive. This is particularly given form in the context of the matter-antimatter problem, which will be the subject of the next episode. However, on the other hand, Lemaître's primordial atom was the product of pure genius given the context of what physicists knew in the early 1930s. The genius for me was in looking at the most powerful theoretical explosion as inspiration. After all, it is very important to remember that the invention of the atomic bomb in the Second World War was still a decade and a half into the future at that point in history. If only Lemaître had been inspired by the largest possible explosion in nature, namely the reaction when matter and antimatter collide. Looking at a positron and electron annihilation, we see a pair of gamma rays travelling away from each other in polar opposite directions. Or if Lemaître had studied how a supermassive star dies, giving birth to a black hole and a pair of gamma ray bursts, each travelling away from each other in polar opposite directions, for that is precisely the inspiration behind the Big Bang Hypernova hypothesis that we shall collectively explore together in this series. But before we get ahead of ourselves, we need to understand the main piece of observational evidence that supports the Big Bang theory, namely the cosmic microwave background radiation. A logical consequence to the fact that space-time is indeed expanding as we move forward into the future is that if we could reverse time and travel back into the past, we would see the metric of space-time contract. Light that is red now contracts, turning first orange and then yellow as its wavelength is contracted. Further to this, after countless observations by astronomers, by plotting the position and velocity of millions of galaxies, we have found that they must have all come from a single point of origin. According to Lemaître's Big Bang theory, all the matter that makes up the universe was, at some point in the far distant past, all concentrated into being inside a relatively small volume. Because of the extremely high density and concentration of both matter and energy being contained to such a small volume, then by the laws of thermodynamics it implies that the very early universe was both extremely hot and dense. Thus, as a result, the prediction was made that if the Big Bang theory were in fact true, then we should be able to measure the residual light energy emitted from the hot and dense early universe. In a manner of speaking, we should be able to see the afterglow of the Big Bang explosion. Another important prediction regarding the nature of light coming from the afterglow of the Big Bang comes from the fact that space-time in the universe has been expanding since the moment of creation. As we have already seen, the wavelength of light is stretched out by the expansion of spacetime. Yellow becomes orange before turning to red. But these wavelengths of light are visible to the human eye. The full expanse of wavelengths of light extends along the full electromagnetic spectrum, with radio waves at one end and gamma rays at the other extreme. The spectrum of light our eyes can see is only but a small fraction of the electromagnetic spectrum. Thus, red light when stretched becomes infrared light. Infrared light, when stretched further by the expansion of spacetime, will end up in the microwave part of the spectrum. Thus, light coming from the afterglow of the Big Bang event, where the universe is both hot and dense, would have been stretched to the microwave end of the spectrum because of the expansion of the metric of spacetime. Putting this together, the Big Bang theory made a prediction whereby, if it were true, then we should see light stretched to the microwave end of the spectrum, coming from every direction of the sky. Up until 1964, when evidence was found for the microwave background sky, the alternative, steady-state cosmological model held dominance. Initially, before the discovery of the expansion of spacetime, the universe was seen as eternal. There was no single moment of creation for everything. Rather, the universe was seen as having no beginning nor end. It was eternal. However, with the accepted discovery regarding the expansion of spacetime, the steady-state cosmological model was modified. In this modification, rather than all matter being created in one single event, as in the Big Bang model, the steady-state model proposed that new matter is constantly being created to fill in the ever-expanding universe. So according to this modified steady-state model, when the universe was young, there was less matter in the universe than there is today. Less matter, hence less stars and galaxies. But critically, the density distribution of matter and energy was the same as it is today. Just that there is less, because the volume occupied by the universe is much smaller. Hence, the very early universe would not be an extremely hot and dense place as it is in the Big Bang cosmological model. As the steady-state universe ages, the volume of the universe expands because of the expansion of spacetime. However, as the universe expands, the steady-state model says that matter is constantly being created at a rate that is proportional to the expansion of the spacetime metric. As matter is created, as spacetime expands, new stars and galaxies thus form from the newly created matter, all the while the density distribution of matter and energy throughout the entire universe remains relatively constant. Robert Wilson and Arno Penzance in 1964, working for Bell Telephone Laboratories at the Holmdel Horn Antenna, were testing their new receiver for use with satellite communication. In testing the capabilities of the receiver, they received an unusual signal. This residual signal appeared continuously with a noise intensity 100 times greater than expected, coming from all over the sky. No matter which way they pointed their telescope in the sky, they always saw this residual signal. Having checked all their equipment, including sweeping out all the pigeon droppings, as well as ruling out any possible man-made or intergalactic sources that could explain the presence of the unusual signal, Wilson and Penzance turned to Princeton University in order to help them find the cause and source for the unusual signal they were receiving. At Princeton, astrophysicists Robert H. Dike, Jim Peebles, and David Wilkerson were preparing to search the microwave spectrum range for the afterglow of the Big Bang event. Burke, a friend of Penzance, informed him of a paper by Jim Peebles about the possibility of finding radiation left over from the Big Bang explosion. Realizing the significance of their accidental discovery, Wilson and Penzance collaborated with Princeton to jointly publish their results in the Astrophysical Journal of Letters. Here was definitive proof confirming Georges Lemaître's Big Bang theory and closing the case for the long-held steady-state cosmological model. Light emitted from the very early universe, around 200,000 years after the Big Bang, now stretched to the microwave length of the spectrum because of the expansion of spacetime, was seen coming from all corners of the Earth's sky. Thus it is that the Big Bang Theory, as we know it today, came to be the accepted story of how our universe came into existence. But, as we shall start to explore in the next episode, in looking at the details, there are major paradoxes and problems that arise in working out how exactly our universe came into existence coming from a small dense point, in particular as matter and antimatter are brought into existence and connect with each other. Until next time.